Welcome to another live session for the online class. The floor is open for your questions. I'm going to guess that there might be questions about a certain exoplanet discovery that's occurred since our last live session, but really you can ask about anything you want.
All right, so we do indeed have several questions about the newly discovered TRAPPIST-1 system. So why don't you go ahead and do a quick overview about what was discovered, and then I'll hit you with a few questions that the students are coming in with.
Sure. The 30,000-foot view, if you like, or the 40 light-year view, is that this is a truly exciting system. There are now close to 4,000 exoplanets confirmed, so a huge number. There are several hundred Earths, Earth-like planets, within a factor of 2 of Earth size or mass. So Earth-like planets and even Earth-like planets in habitable zones are not unheard of. So a few thousand exoplanets, a few hundred Earth-like exoplanets, and a few dozen that are Earth-like in their habitable zones. But in this one system, we find 7 terrestrial or Earth-like planets, 3 of which are in the habitable zone of their small dwarf star. So it's a pretty exceptional system, even within the context of dramatic improvements and growth in the field of exoplanets.
All right. So our first question is, when we see an artist's impression of, for example, of the TRAPPIST system, how realistic are they and how are they created?
Many of these artist impressions are commissioned by NASA. So NASA facilities. The TRAPPIST-1 system is, of course, was given its name because of a telescope that the Belgians operate in Chile. The TRAPPIST is an acronym about transiting planets. I can't remember all the words in it. It's also an allusion to the Trappist ale that is very popular in Belgium. But NASA was heavily involved in this research because the Spitzer Space Telescope did a long sequence of continuous observations that nailed a lot of the orbits and a lot of the exoplanet candidates. So NASA employs space artists and illustrators, and they've illustrated all sorts of things that come from NASA science. In the case of an exoplanet, they try and make it as realistic as possible. So the basic parameters for this system are that the star is a red dwarf. It's about 8% of the mass of the sun, which actually just puts it on the bare edge of being a star at all, much less massive than that, and it would just be a hot ball of gas with no fusion. It is about 2,000 times dimmer than the sun. Obviously, it's very red because it's very cool. And so the artists try and represent a very small, red, dim star as the dwarf. Now, it is hard to represent the true distances of planets along with the true sizes of planets and stars. If you make a solar system scale model, that becomes very clear. And the same problem exists in this system. So most of the artist illustrations that show both the star and the planets are not realistic. They're not to scale, basically.
Right. The next question is from Rami, who's on with us live. How can the orbital mechanics of TRAPPIST-1 system stay stable for such a long time around a long-lived brown dwarf? And do the planets stabilize themselves? How does that work?
So it's a red dwarf, not a brown dwarf. Brown dwarf will be a substellar object, and this is an actual star, but a very dim one. So it's a red dwarf, and the orbital parameters are very well measured by the observation. And there are 2 striking features of the orbits of these planets. First of all, they're extremely close to their star. The orbital times of the 7 confirmed planets vary from about 2 days to 2 weeks. So remember, Mercury is the fastest planet in the solar system with a 3-month orbit. So these exoplanets are very close to their parent star and move very fast, according to Kepler's law. That, of course, in turn indicates that the tidal interaction between the red dwarf, and the planet is going to tidally lock these planets. So all 7 of these planets are in the grip of their parent star to the level where they point the same face to the star as they orbit it, as Mercury does, as the moon does with the Earth. So that's one thing we know. Very tight, fast orbits, tidally locked. The other thing is that the orbital periods have ratios. When you look in the paper, the numbers of days of the orbits are fractions of days. But if you take the ratio of the 7 planets' orbits to each other, all those ratios are ratios of whole numbers. And to a dynamicist or planetary scientist, that indicates that these planetary orbits are in resonance. So these planet orbits are interacting with each other. It's a different version of tidal locking, if you like. That in turn also indicates that this is not a long-term stable situation. And so in models of how planets form and evolve, it's almost certain that these planets formed further out, or perhaps out at more reasonable distances, like a Mercury distance from the sun, and then gradually migrated in. And then as they reach this stable position of tidal locking and orbital resonance, the ratio of the orbits being whole numbers, then they stabilize. Is it long-term stable? Not necessarily. This probably will persist for some tens or hundreds of millions of years. If you ran a model, you'd show something like that. But I doubt that it's stable for billions of years. And remember, the red-dwarf star lives billions of years, a lifetime far longer than the sun. So this is not a long-term stable configuration. These planets will eventually, almost certainly, migrate in and be swallowed by their dwarf star.
All right, the next question is, why do scientists compare the TRAPPIST-1 planets with Galilean moons, and how will we get to know of the existence of any life forms present there now or present in the past?
It's a good question. I mean, they compare the TRAPPIST system to the moons of Jupiter because in a sense, in terms of the mass of the star, the size of the orbits, and the mass of the planets, the system is actually closer to Jupiter plus its moons than it is to the sun and the planets. So we've already seen that it's far tighter in their orbits. And also these objects are Earth size or smaller. I think a couple of them are less than half the size or mass of the Earth. Now, Jupiter doesn't have any moons that are as massive as the Earth, but the largest moons of Jupiter and Saturn are more massive than the moon, the Earth's moon. And so they're in the realm of sub-Earth sized objects. And also their orbital periods and proximities to their star are more in line with moons of a giant planet than they are with the solar system. And finally, the star, because it's 10 times less massive than the sun, is somewhere in the middle range between a Jupiter mass and a sun mass. So it's completely legitimate to compare it to a Jupiter system. I forget what the second part of that question was.
Oh, how will we know if there is life? How can we learn about life that's present there now or in the past?
So the second distinct question, and important and worthy of a full answer itself, the issue of life on these planets. So habitability is a term that it's received some pushback in the research community because in both scientists and definitely in the popular media and the press, the word habitability is used kind of loosely. It implies that biology could exist on these planets. And the problem with that is that all the information we have is the nature of the orbits and their distance from the star. So when habitability is used in the terms of this TRAPPIST system, it's based on the fact that at the surface of 3 out of these 7 terrestrial planets, the radiation from that dwarf star is close to the radiation that we receive at the Earth's surface from the sun, which means that liquid water on the surface of one of these planets could, in principle, be liquid. First of all, we don't know that there's liquid water there at all. Second, we don't know what the atmospheres of these planets are or whether they have atmospheres at all. And the atmosphere obviously affects the surface temperature because many of the gases, as on Earth, are greenhouse gases, so create a higher temperature and perhaps too high a temperature for water to be liquid. So these are huge uncertainties and unknowns. So talking about habitability is fairly tricky. Also, while we think the orbits are stable and coplanar, in other words, they don't have a large eccentricity that would give dramatic seasons that might make a planet uninhabitable, we simply don't know. We don't know what the orbital tilt of these planets is. The eccentricity of the orbits does seem to be small, and that's partly because they're tidally locked. So habitability is uncertain, basically. It's just a general framing of a liquid water argument. As for life on the planets, that would take an entirely different type of observation, a much more difficult observation that involved gathering the light, the feeble reflected light of each of those little planets and spreading it out into a spectrum. The observations so far have not done anything of that sort. It is very difficult to directly observe these tiny exoplanets, even though they're only 40 light years away.
All right, so the next question related to these exoplanets is how or when or do you think that mankind will ever be able to send people or machines to this system?
So the proximity is a relative thing. Obviously, the nearest star systems are a little over 4 light years away. So this system is almost 10 times as far as the nearest stars. That still puts it in the solar neighborhood. It's definitely in a the Milky Way is 100,000 light years across. So 40 light years is a small distance compared to that. So these are planets that are in our backyard for sure, but they're not the closest planets we might find. They are just tantalizingly close enough to even consider sending robotic probes there, by which I mean miniaturized probes. The Breakthrough Starshot project has put on the table an idea to send nanobots powered by solar sails to Proxima Centauri, to the nearest star system, which is likely to have terrestrial planets, but we don't know as much as we do about the Trappist system. And that technology is designed to accelerate a tiny mass probe up to maybe 5, maybe 10% of the speed of light, using the solar power and then coasting to get to the system. And so 4 light years away at 10% of the speed of light is 40 years to get there. So you do the same thing to the Trappist system and you're talking 400 years, and in practical terms more like 1,000 or more years. So we are on the verge of technology that we have available to us now that could get miniaturized probes to this system within a millennium. Whether that is of interest to people or whether it's motivating enough to actually do it is an open question. Obviously, light is the fastest thing there is, and so it would be, once you get to the system, to get the information back about what's happening on those planets would only take 40 years.
All right, so the next question is, what light does this discovery shed on the origin and formation of our own solar system?
That's a good question, and it's not really known yet. Only in the last couple of years have exoplanet researchers sort of opened their horizons. The first decade and the even first 15 years of the subject, starting in 1995, involved doing the most obvious thing, which is looking for planets around sun-like stars, since we know our system has 8 planets and a few dwarf planets. So that was the work of exoplanet research for the first period of time, until it was realized legitimately that there are many more dwarf stars than sun-like stars, so why not look around dwarf stars for planets? And even before the Trappist system was discovered, there are a number of surveys underway to look for planets around dwarf stars. And those surveys had already projected that there would be roughly 1 planet of any kind around each dwarf-like star. So because most of the stars in the galaxy are dwarfs, that implies a very large number of planets in the Milky Way. What this discovery does is it shows a large number of terrestrial planets around a dwarf star. And if these statistics hold true, and you can't extrapolate from a sample of 1, but it's very intriguing, then there would literally be hundreds of billions of terrestrial planets in the Milky Way, almost all of which are orbiting dwarf stars like this one. So this would then become a typical situation for a planet.
All right, the next question is, what is the protocol that will be followed in case an intelligent life form was discovered in the Trappist system?
So the Trappist system has, of course, moved into the spotlight, not just for possible detection of life by looking at the atmospheres of these small planets using ground-based and space-based telescopes, but also for SETI, Search for Extraterrestrial Intelligence. The Allen array, which is the largest array of radio telescopes trying to do SETI work in Northern California, has already has amongst its targets hundreds, perhaps thousands of red dwarf stars. So they're following the same strategy that, much of the terrestrial and habitable real estate could be around dwarf stars. So this just moves to the top of their target list, if you like. So obviously, these telescopes, radio and optical telescopes, are going to be trained on this system, increased, dramatically so in the next few years. And if there are artificial radio signals emanating from civilizations on any of these terrestrial planets, these telescopes will find them. And those signals don't actually have to be intrinsically very weak, because the sensitivity of these telescopes is so great. They could detect fairly feeble radio emission from civilizations on Earth-like planets in the Trappist system. So it's going to be an interesting experiment. It's a shot in the dark because there's no reason yet to believe there's even life on any of these planets, let alone civilizations, but it's an experiment worth doing.
All right, so at this point, we're moving away from questions about Trappist. And the next question is from someone who is on with us live. And they ask, what will be the next technological breakthrough in astronomy?
And that's a good question. It's hard to predict sometimes. I'll just say where the technical innovation is happening right now. A lot of the technical innovation in the last 5 years or so and into the near future is adaptive optics. It's sharpening up the images from ground-based telescopes to essentially cheat the atmosphere and take images as sharp as if the Earth had no atmosphere or you had a telescope in space, which is an incredible gain. That technology is fairly mature, so I put that in the rearview mirror. As far as next generation technologies, it's a little hard to predict. Possibly one would be a way of making super thin, super light mirrors, even though, including at the University of Arizona and also in the University of California, even though there are methods for making large mirrors much thinner than they used to be in the golden age of the Palomar and Lick observatories, these mirrors are still large. The Giant Magellan Telescope, there's 5 tons of glass in each of the 7 mirrors of that telescope, and then you have to put it in a huge, heavy, massive structure. If it were possible to make really light, super thin, super light, large mirrors, then both ground-based and space-based astronomy would benefit. The lightest material people have experimented with is beryllium. Beryllium, obviously a very light element. It's stiff, it's rigid, but it's also brittle. It's a very hard material to work with. So I think the material technology to let mirrors be made much lighter than they are now would it might let amateur astronomers start to work with multiple meter diameter telescopes, which is not possible at the moment. It might let astronomers break the barrier of 10 and 20 meters and build 100, 200, 300 meter telescopes, which would be amazing. So that's the one technology I would identify. The other one, of course, is based on detecting non-traditional forms of information from the universe. Almost everything in the universe is electromagnetic waves. The frontiers for non-electromagnetic information from the universe are, of course, gravity waves, detected for the first time only about a year ago. Neutrinos, detected from the sun and a handful of other celestial sources, and cosmic rays, which have been detected for actually almost a century, but it's not possible to do astronomy with narrow beam telescopes and cosmic rays the way we can do optical astronomy. I suspect there'll be technologies coming that will let us do all of these kinds of astronomy, in particular neutrino and cosmic ray astronomy, much better than we can now. And these will require technological and detector innovations.
So next question is general about the Drake equation, but then I think it's a good opportunity to talk about the state of our knowledge of each piece. So it is, please tell us about the Drake equation and what is the current state of our knowledge of each of the factors.
So the Drake equation, to remind people, is a formulation that started with Frank Drake in 1960. I think there was a conference at Green Bank at the Radio Observatory where this young researcher, he was a postdoc at the time, went to the board, and just to lead a discussion on life in the universe, he wrote in real time this equation, which is a series of numerical factors, 7 factors, which multiplied together gave the N, the number of intelligent communicable civilizations in the Milky Way at any given time, who we could talk to with technology. That's the Drake equation. And in the last decade or so, substantial progress has been made. The Drake equation is a series of factors that range from the purely astronomical. The first term is the rate at which stars form and therefore planets in the Milky Way. That number has been known for half a century and it's pretty well determined now. Followed by planetary factors, which involve how many how many planets per star system are there, and how many potentially habitable planets are there per star system. And we're very close to the Kepler mission and surveys of red dwarfs and so on to putting a firm number on those 2 factors. So that means three factors, the first three factors of the Drake equation, are essentially known. They're not going to change much. And thereafter, the last factors are completely unknown, because the next one is on what fraction of those potentially habitable planets does life actually occur? And we simply don't know. This is the issue of habitability and how often that leads to biology. But it's probable that within 10 or 15 years, we'll measure that number too. That's the next one. And of course, the detection of life beyond Earth will be part of that. The last three are even harder. It's the fraction of times that life goes from being microbial, or the beginning stages of life, to being intelligent, the fraction of times that that intelligent life develops the technology to leave its planet or communicate with the rest of the universe. And the final factor is a time. It's the lifetime of a civilization in a communicable state, such that we can do SETI and talk to them. And we simply have no idea of those last four factors. The fourth one, as I say, we may measure in a decade, but the last three, not at all. And we'll have to actually detect intelligent life in the universe to know the answer to the Drake equation.
All right, our next question is from a live viewer, and it is Mars worth colonizing?
And that's a big question, and people are actually starting to debate it now. There are obviously fairly steady but slow-paced efforts by NASA to bring back samples from Mars, then to send astronauts to Mars, then to build the rudiments of an initial base that may only hold 3 or 4 people for limited periods of time, so they're not there forever, living and dying there, and then eventually a colony. But NASA is not even projecting to a Mars colony. They simply don't have the budget or the means to do that. And even the stages I talked about are 20, 25 years away. So there are other entities that are possibly thinking more aggressively of Mars colony. Elon Musk and SpaceX is the most well-funded and the most well-known. He's already made a proposal and has some of the engineering figured out for an interplanetary transport ship that might carry hundreds of people on journeys of fractions of a year or a couple of years to Mars, and enough supplies and enough people to inhabit a base, a moon base of dozens of people or maybe 100 people. The cost of the infrastructure to set up the base is phenomenal, so it's not clear how this would be funded. Musk himself does not have a viable economic model for how Mars colonization would work. So big corporations or governments would have to be interested in it for it to happen, because the price tag of even a minimal Mars colony, which is one that's not fully self-sufficient and is resupplied from the Earth and does its best to gather materials like oxygen and water from the Martian soil, the cost of that are trillions of dollars, probably tens of trillions of dollars to set it up. And world GDP is $8 trillion. So it's not a ridiculous amount of money, but it's extremely expensive. So I think Mars colonization by any means is 50 to 60 or more years in the future.
All right, and we have another Trappist related question, and it is from Rawan, who is on with us live, and it asks, can you tell us more about the future telescopic missions that will want to observe the system, and what can we learn, and can today's technology detect life there if present?
These subsequent observations are extremely interesting, because really there are capabilities on the horizon, the near horizon, a couple of years to 3 to 5 years, that have the potential to sniff out life on one or more of these Earth-like exoplanets. What you have to do, of course, the Trappist planets were detected indirectly. All these telescopes in the paper that was published in the news stories are based on staring at that dwarf star and just looking for little dips in its brightness. And there are a lot of dips, because there are 7 planets crisscrossing its face and dimming it by different amounts that depend on their size. So that's all indirect. You've never really seen the planets themselves. The next stage involves imaging the planets themselves, which means you have to separate their light, their much, much fainter light, from the light of the parent star. Now you're helped in that regard by the fact that the star is a red dwarf, so the star is very dim, like I said, 2,000 times dimmer than the sun, whereas the planets are Earth-like, and so they intercept a significant fraction of that starlight. And also they're much closer to the star, so they intercept proportionally more of the starlight than the Earth does at the Earth-Sun distance. So that's in the positive direction. In the negative direction, they're also a lot closer because they have orbital times of a week or two rather than a year. They're very close to the star, so that gives back some of the gain you had from the star being dim. It's a trade-off, but they are easier in the aggregate. With all those things taken together, they are easier to detect than an Earth orbiting a sun at the same 40 light-year distance. So that's very exciting. The other exciting thing is that the biomarkers, that is the atmospheric tracers you would want to see to show that there was microbial life on a planet, essentially oxygenic photosynthesis, generating oxygen as a waste product, those markers have very strong signatures in the infrared part of the spectrum. And the reason that's important is because the star is hotter than the planet. And so the contrast of the planet relative to the star is better in the infrared. So these are easier experiments to do, the biomarker detection experiments, easier to do in the infrared than in the optical. And that maturity of technology is available to us. So the James Webb Space Telescope has an infrared spectrograph. It has a way to occult the light of the star and separate out the light of the planet. And so undoubtedly this and other systems are prime targets for James Webb Space Telescope. But James Webb was never designed for this particular experiment, and so the range of spectral coverage it can get is fairly limited. These still are very faint targets, so it'll take a lot of James Webb Space Telescope time to even observe a handful of systems. People are also building ground-based telescopes that have that same capability through adaptive optics to blank out the star, including our Giant Magellan Telescope being constructed in Chile. So using adaptive optics, using infrared, near-infrared technology, ground-based telescopes can do this same experiment. James Webb is a 6.5-meter telescope in space, or will be in October 2018 when it's launched. But there are much bigger telescopes on the ground now, and even in the future will be 20. Our telescope is 22 meters. There's Caltech are planning a 30-meter telescope, and ESO, European Southern Observatory, also have a 30-plus meter telescope. So with 10 times the light gathering power on the ground, these are easier experiments to do on the ground if you can sharpen the images. And this will happen also in about a 3 to 5 to 6 year time scale. There are also other space missions that are on the drawing board, and those may not happen quite as quickly, but within a decade. So there are going to be more than a couple of different ways to do the life detection experiment within the next decade, making it a very exciting prospect.
All right, the next question is, sorry, I got lost in my list. What is the most scientifically accurate movie up to date?
About astronomy, that's a good question. There have been some pretty good ones. I mean, I've been to websites and seen articles that, kind of grade movies and rate them and critique them based on science content. In the last few years, The Martian pretty much wins that contest because the Andy Weir, who wrote the book on which the movie was based, was a consultant on the movie. I don't think he actually wrote the screenplay, although he might have done. And so the movie pretty much got it right for the most part. And even places where it shaded the truth, like in the initial storm, where the thin Martian atmosphere in practice could not have had the violent effects that it's shown to have in the movie. That was in the book too. So that wasn't a flaw of the movie. That was a flaw of the book that the author acknowledged and the movie continued and represented. So The Martian pretty much wins for me in the last handful of years. But there have been other, reasonable movies. Interstellar had Kip Thorne as a scientific consultant. He's probably the most well-esteemed gravitational theorist in the world, and he was a script consultant on Interstellar. And Interstellar also took some, artistic license with some issues, but also got a lot of things right. And some of the visuals in Interstellar were actually based on supercomputer simulations done specifically for that project by Kip Thorne and his Caltech group, some of which even led to scientific discoveries and research papers. So I would put Interstellar right up there too. So pretty much in the last 5 years, those are the two top ones for me.
All right, the next question is about galaxy rotation. What does the flat rotational curve mean? Does this Does everything in the galaxy orbit the center at the same rate, or does it just orbit at a different rate than Kepler's laws would predict?
It does orbit at the same rate once you go out from the center, and that is very different from what Kepler's law would predict. So what does flat rotation curve mean? It means that if you measure the motions of objects, test particles, stars, or gas clouds moving out from the center of a galaxy like the Milky Way, any spiral galaxy, you can measure their velocity, the velocity with which they orbit the center, their circular velocity, because these are circular concentric orbits. And obviously at the center, there's no net motion. The center isn't going anywhere. And as you move out, there's what's called a flat rotation curve, where in the inner part of a galaxy like ours, or any spiral galaxy, the velocities increase linearly with distance going out smoothly. And then well before you get to the distance where the sun is, those velocities reach a maximum and then sort of flatten off. And if you keep going out further and further in the galaxy, measuring the speed of stars and gas, the velocity doesn't really change. In a big spiral, in the most massive spiral galaxies, that velocity ramps up to about 200 kilometers per second and then just stays flat. And that's really hard to understand. It stays flat to as far as you can see the galaxy, right till you've reached what seems to be the visual edge of the galaxy, and there's hardly any stars or gas to trace its rotation. It's flat. Why that's surprising is by thinking about the solar system rotation. So in the solar system, essentially all the mass is in the sun, 99.9%, and the planets all follow orbits which vary according to Kepler's laws, with the cube of the period proportional to the square of the semi-major axis, or the distance from the sun. So those periods go up as you go out. And so you have 88 days, 3 months orbital period for Mercury. You have a year for the Earth, obviously, and you have 84 years for Neptune. So those orbits are just getting much slower the further out you go in the solar system. And that's because in Kepler's law, they're all responding to the mass of the sun, which is essentially all the mass. The only way you could explain orbital periods not going down according to Kepler's law is if somehow most of the mass of the galaxy is distributed on large radial scales so that it's driving these fast motions. You just essentially have to say that when you've moved out beyond the center of the galaxy, where the majority of the mass should be, and certainly to the visible edge of the galaxy, where all the mass should be if it follows the stars, if those velocities aren't going down by that point, then there must be more mass outside the visible galaxy than inside the visible galaxy. And that was the argument for dark matter starting in the mid to late 1970s with the work, I'll say, of Vera Rubin, who died just a month or so ago, and who many people think should have got the Nobel Prize for that insight.
All right, the next question is from a live viewer who asks, are there mountains of metal on old, colder stars?
So that's an interesting question. I mean, older evolved massive stars do actually make heavy elements, including metals. And the core of a red giant star late in its life is a sort of onion skin scenario where, but this of course is a strange state of matter because it's a gas, it's a very high temperature gas, a plasma, all the electrons stripped off all the nuclei. And in the center parts where the temperature is really high, by which I mean hundreds of millions of Kelvin, perhaps a billion Kelvin, then the fusion is able to make metals, can make nickel, can make iron, iron is the most stable, so that tends to be where the fusion stops. So you have the center of giant stars that are cores of iron, but they're not a solid, they're not a, not a rocky metallic core like you have in a planet. It's a plasma, a high density plasma. It's denser than normal matter actually, even though it's essentially a gas, a very hot gas. So no, there are not mountains of metal in stars. There are extremely hot plasma cores of metal, iron in particular, at the late stage of a star. And that's a very strange state of matter indeed.
All right, the next question is back to TRAPPIST-1. What are the chances of life surviving the strong stellar winds, magnetic field, and radiation on planets, such planets extremely close to TRAPPIST-1?
So this is a good question because it gets back to habitability. What's a more nuanced way of talking about habitability beyond calculating the solar or the star radiation at the surface of a planet and asking, does it create a surface temperature above or below the boiling or the melting point of water? To go beyond that, you do need to know more about the environment. You need to know the orbit. You need to know the inclination, the tilt, the orbital tilt of the planet. That's hard to measure for exoplanets. You need to measure the eccentricity. That's easier to measure, and in this case, eccentricity is low, nearly circular. So not strong seasonal variations. We don't know what the atmospheres are made of. That's an experiment that will be done, we hope, in the next decade. And then the other thing, as the question alludes to, is that the environment could be inhospitable for life just due to the activity of the star. The sun has, of course, solar activity, solar storms, flares, super flares, occasionally. And dwarf stars, red dwarf stars, are even though they're feeble fusing stars, they're not uneventful. They still have magnetic fields. They still have storms and hot spots. And because the planets are so close to that star, yes, that stellar activity could, in the chromosphere or the corona, could impact the environment of the planet, unless it's shielded by its own magnetic field. Remember, the magnetic field of the Earth is what shelters the Earth from high energy radiation, from cosmic rays and UV and so on, where Mars, not having a strong magnetic field, is dosed with radiation, and that makes Mars a little less habitable. Its soil is sterilized, for example, by solar radiation. So we simply are at a too primitive a level of our knowledge to understand how these environments are in terms of true habitability. All these effects, the question asked about, are really important to go beyond a sort of zeroth order or kind of very schematic way of defining habitable.
All right, the next question is from a live viewer who asks, can you describe some of the tools that ancient astronomers, the Mayas, Incas, civilizations used to make such accurate predictions of eclipses and other astronomical events?
Yes, it's a good question because some of their observations were extremely good. The Babylonian calendar 5,000 years ago was better than any calendar until the Julian calendar of the great peak of the Roman Empire in 40 AD. So these civilizations obviously knew what they were doing to have a calendar accurate to a minute or two in a year 5,000 years ago. So these early fixed civilizations, the Sumerians, we don't know quite as much about them, but the Sumerians, the Babylonians, the Egyptians, those great civilizations from 4,000 to 5,000 years ago or more, all did careful observations of the sky and the stars. And their methods were very simple. They obviously built what you would call observatories, but they're not like a modern observatory. They built structures where people could make observations with sight lines, you could align slots in nested walls to make observations of a particular direction. You could create a observation station with a horizon, an artificial horizon that you create, that you can make your measurements with respect to that artificial horizon. There's good evidence the Mesoamericans did that, the Mayans, the Incans, 1,000 years or more ago. The Egyptians and the Babylonians used all of these methods. They obviously had metal, so they could make sighting, they could use plumb lines and create angular scales, because the Babylonians, of course, gave us our angular scale. 360 degrees in a circle comes from the Babylonians, so they were making angular measurement, and that angular measurement with simple sighting devices on the sky gave them the accuracy of their calendar. It also let them make star catalogs and put the positions of stars in place, not as accurately as with a telescope. They had naked eye, but pretty good. So these were very sophisticated methods, and the key to having a precise calendar or having an accurate star catalog when your measuring devices are fairly primitive or naked eye is repeated observation. And with the case of the calendar, you make repeated observation over many years to refine your timekeeping to get a very accurate calendar.
All right, the next question is below my threshold. Oh, what research is currently being done about dark energy?
What research? Dark energy is in a tricky situation now. It's the biggest unknown in cosmology. It's the biggest cipher. The two major ingredients of the universe are dark matter and dark energy. Astronomers do have some leads on dark matter. We don't know what it is, but there's some decent ideas, some of which stem from particle physics and our theory of the fundamental nature of matter, and some of which are observational, where we have observational ways of diagnosing dark matter in the universe on different scales and understanding its properties at some level beyond its gravitational effect. We can understand its electromagnetic interactions, if any. We can understand indirectly the mass of whatever subatomic particle the dark matter particle might be. So those observations are proceeding, and there are also lab experiments. Some of these are underground to shield from cosmic rays, but there's a series of lab experiments, a few on desktop, but mostly using fairly large detectors deep underground that are trying to measure dark matter particles directly. So that work is progressing, and it's not yet at fruition where we've ruled out or obviously discovered. You read about it on the front page of all major newspapers if dark matter was discovered. But we're starting to be able to rule ideas out. Dark energy is not in the same situation at all. Dark energy is the dominant component of the universe that's responsible for the cosmic acceleration discovered in 1995 and confirmed since then. There's no doubt that the universe is accelerating. And so that hypothesizes an entity working in the opposite way to gravity with some pressure that essentially drives space-time ever faster and faster apart, creates new space at essentially an exponential rate. What could possibly do that? There's essentially no force in physics that's known to be able to do that, even though vacuum energy is a concept that physics has. Vacuum energy, when you work it out with standard physics, doesn't get you where you need to be to explain an accelerating universe. So standard physics is not able to explain dark energy. And so there's a lot of very clever and exotic theoretical ideas on the table. And the problem for the field, and why you probably don't read many articles about progress in dark energy, is there isn't much progress. These theories are kind of wild and all over the map, and there's lots of them, and we don't know how to choose between them. And the observations are kind of stuck. The observations of dark energy, beyond saying that the universe is accelerating and showing that it accelerates the same amount in each direction you look, and maybe that the acceleration hasn't changed over time, going beyond that is extremely difficult, and people simply don't know how to do the observations to sort of home in on what dark energy is.
All right, next question is, do you see interplanetary commerce happening one day? For example, helium-3 tankers going from gas giants to Earth.
I see it someday. I see it within a century. I think the commodities that exist in space have a lot of intrinsic value. The question asked about helium-3. Helium-3 is an important and a rare isotope of helium. It's very expensive to make on the Earth by manufacturing techniques, and it exists because it's created sort of in situ on the surface of the moon and other airless bodies. You could, in principle, mine helium-3 on the surface of the moon or elsewhere in the solar system and harvest that and send it back to the Earth, where it has a large intrinsic value. The other commodities, if you like, minerals that are high value on the Earth, and some are finite resources and diminishing, are precious metals, platinum, famously used in catalytic converters, but in a lot of industrial techniques, and rare earths, used heavily in the semiconductor industry. So Earth, certain types of asteroids, near-Earth asteroids or small rocky bodies in the solar system have both platinum group metals and rare earths in substantial quantities, and so mining those and shipping them back to the Earth where they have high value is not an unreasonable thing to do, and people have started to make business models of it. There's the innovator's dilemma, of course, because if you don't have the infrastructure to harvest these metals, mine them, and get them down to Earth cheaply, then the costs of doing that business are just so high you could never get started. You'd just be having to invest so much up front that you would essentially go out of business before you saw revenues. So it's not totally clear how the business model will work in terms of getting it off the ground, because the governments are not going to subsidize this. This is going to be the private sector. But the truth is, it'll probably happen. And it won't happen soon. It'll happen in a few decades.
All right, the next question is, How is liquid water detected via telescope?
So water is a fairly abundant ingredient in the universe. It's one of the more common molecules. I can't remember the ranking. I think it may be the fourth most common molecule in the universe after carbon dioxide, carbon monoxide. I'm not sure what the third one, methane may be more common than water, but it's in the top 5. So water, H2O, in whatever form, can of course be solid, liquid, or gas, is a fairly abundant material. And detection of liquid water, or detection of water at all, is based usually on its vibrational transitions. As with most molecules, you're not looking at the simple spectra of electrons changing their energy state, as with a single atom, producing sharp spectral features that are like a fingerprint of that element. With molecules, they have so many modes of oscillation and vibration. The energies of those changes of vibration and oscillation are low energy, and so they put rather broad spectral features, or bands, molecular bands, into the infrared or submillimeter part of the spectrum. So water is routinely detected in the universe, either in the solar system, in star formation regions, in external galaxies. I think water's now been detected in a galaxy 12 billion light years away, is using radio techniques, radio spectroscopic techniques. And in almost all these cases, the water that's seen is hot. It's kept in its sort of hot state, so it's a vapor, or steam, if you like, by this light from stars. Detecting water on a planet, in the atmosphere of a planet or on the surface of a planet, would equally be done with spectroscopy, but there you'd be looking at the reflected light from the planet itself, and that experiment hasn't been done yet.
All right, this I think will be the last question for today. We have to end a little bit early, unfortunately. But the question is, are there any realistic plans to plant life on other planets, and what would be the pros and cons of such a project?
So this is interesting because it alludes to a sort of philosophical debate amongst astrobiologists, and I've been at a meeting where a whole session was devoted to this. The question of, should we seed life in the universe? There's a question of detecting life in the universe, and then there's colonization, which is where we go and plant ourselves as life forms. But it's also possible to see if life could take root on a planet, and that's an interesting thing to do because you learn about the limits of biology by trying to do that. And I would say there are actually quite violent, almost violently diametrically opposed views. So Chris Impey, who's a very esteemed astrobiologist at NASA Ames, he has argued to do this. He's argued that if we could find an extremophile, or even a plant, a super hardy plant or fungus or some life form that would somehow grow on Mars, or even the moon, I think that's less likely, but let's say Mars, if that were possible, we should do it, because we'd learn so much about the limits of biology by seeding life on Mars if we could do it. And doing genetic engineering maybe to find that life form. So there's a school of astrobiology that says we should do it because of what we would learn. There's another school that says we shouldn't mess with the planets. It's sort of like the national park argument, that leave no footprint, leave nothing behind. NASA has taken great pains actually with its planetary probes to sterilize them, both on their way to the planet. Sometimes this happens naturally as they go through the atmosphere, they get sterilized if it's a lander. And to clean up after themselves. So NASA is under fairly strict guidelines now and in the future to not contaminate the objects it visits with its probes and landers. So NASA's sort of taken the conservationist end of this spectrum. But there are astrobiologists who argue we should try and seed life on anywhere where it might take root. And I think that's all we have time for today. Great questions as always, and we'll be back with you in a couple of weeks.